Welcome back to page 2 of our Lake Michigan case study, and we're hearing back from Aunt Flo, who works in the DNR. She is responding to Flora's email. So, Aunt Flo writes, "Great to hear from you. Yes, the algae in question are called Cladophora," and I'm going to highlight that, glomerata, Cladophora glomerata. Let's take a peek at this, and I'm going to do that by switching slides. So we see indeed that Cladophora glomerata is green, like we had kind of expected, something that's going to be plant or primary producers. And we have some macroscopic views, so some big picture views, and we have some microscopic views represented here. When we look at the macroscopic one, so this is what I would consider a macroscopic large, it looks like a lot of the big greenery, the fluffy stuff that we see in lakes, kind of diffuse. The microscopic, so if you had a hand lens or if you even put it underneath a microscope, we start to see the inside of the cells, and this one right down here gives me a good image of the inside of the cell. It looks like there's little jelly beans, little green vacuoles in the inside. And that's where you'd have your photosynthesis occurring. So these are definitely primary producers that make their energy from the sun. So now we know what our Cladophora looks like, Cladophora glomerata. It looks like it grows on rocks just out in the water along the shore and has a long history here in the Great Lakes, but has recently become a problem again for many beaches. So she alludes to this was a problem at one point, went away, and here we have it again for many beaches across the basin. Back in the 1960s and 70s, a large increase in phosphorus pollution, so she's talking about phosphorus now, in the Great Lakes causes the algal growth to proliferate. So proliferate, another word for proliferate is to increase or multiply many times. Pretty much out of control is what it implies. Phosphorus is a limiting nutrient for alga in freshwater ecosystems. So what they're saying here is this is going to be something that we're going to see on a chart down below or a table or a graph. So that's going to be what things are responding to, is the amount or the change in nutrient value. So in the 1970s, there were some laws that were enacted, and that decreased how much phosphate was allowed to go into the water. So if we're going to place some laws in to limit in the 1970s, so let me go back and highlight some dates here, we may not see the effects right away. Let's find 1975 on our graph, so that's the start of our axes. So if we had our laws coming in, and I'm going to draw a line right here, right before the 1980s in yellow. Now that I've written my line in, I can kind of blur my eyes and see that there are more points, more data points on the left side of my yellow line that are higher on the page. So we're just going to go with where they are in general. On the right side of the yellow line, there are many ones that were lower. Let's go along and blow up the graph into a higher magnification and really start to deconstruct it. So the first thing we look at when we are graphing is what do the two axes have to tell us and what data should be where. First, we always start with our x-axis, so that is our bottom axis that is horizontal. So I'm going to label x right here, that is our x-axis, and our vertical axes, so up and down, that's always our y-axis. So I'm going to put a y on that. X-axes are always our independent variable. Independence meaning it's independently marching onwards, we cannot change it. And lo and behold, yes, we have year represented on that x-axis, and you cannot change time unless you have maybe a phone booth or something fabulous like that. But no, time is going to march on, and it's going to be independent. So I'm going to label that independent. Okay, and our second axis that's going up and down, so our y-axis or our vertical axis, is going to instead have something that is going to depend on the year. So phosphorus is going to be dependent. I want you to notice here we have total phosphorus. And so does it make sense that in the 70s we saw high values of phosphorus, and then after the 70s, when the legislature came in, so the new laws came in, we saw a decrease in phosphorus value? So kind of looking right across here. And in fact, if I was to draw a line and try to differentiate low versus high, I might want to kind of look at these points right here and how they're grouping and say, hey, maybe this is kind of where I'd separate the low from the high. So over here, we'd consider that high phosphorus. And over on this side of the line, I'd probably say a low phosphorus value here. And when we have low phosphorus, anything below, say 5,500, we do not have algal blooms. Now, previous to this, if we go back to 1975, and we have those higher levels of phosphorus, maybe above 5,500, say, yes, we do have algal blooms. So, let's keep going with our questions here. Number 3 says, examine the figure below and predict what the data would look like if the phosphorus in Lake Michigan is the cause of the recent excessive growth, parentheses, bloom, in algae. Now, I know that our graph tops out here in 2005, but, work with us here on this case study here. Use your imagination. If we started seeing algal blooms, and algal blooms are because there's a high amount of phosphorus, we would probably imagine that now we're seeing something like this in terms of phosphorus. So some numbers up here, and they might bounce around a little bit. Doesn't really matter, but they are above that 5,500 line. So you might project and increase this direction. So, to really cut to the chase, if I had to draw in a big, bold line here, I would make sure it was up and pointing to the right. That's what I would hypothesize as our data.